Just like merge sort, quicksort is a sorting algorithm based on the idea of divide and conquer. Quicksort begins by choosing an arbitrary item to be used as the pivot. How this pivot is chosen doesn't matter. The sequence is then partitioned so that all items less than the pivot are in one sequence, and all items larger will be in another. If an item is equal to the pivot, it will go in the same sequence as the pivot. Quicksort will then be called recursively on the less than and greater than sequences. Starting with the less than sequence, we again choose an arbitrary pivot and partition the rest. A sequence that has one or no items is already sorted, so calling quicksort on it won't change anything. When we have both sequences sorted, we can concatenate them, putting the less than sequence first, then the pivot, and then the greater than sequence. We return this sequence and again have two sorted sequences, so we concatenate and return. Now that we've sorted the left side, we move on to the right. After this has also been sorted, we once more concatenate the sequences and we're finished. Let's say for ease of implementation that we choose the first item to be our pivot. If given an already sorted sequence using this strategy, all of the remaining items will end up on one side of the pivot. And then when this sequence is sorted again, all items will again end up on one side. This ruins our idea of dividing and conquering if we can't properly divide it. The average runtime for quicksort is big O of n log n. However, when the pivot ends up being very high or very low in the sequence, this runtime is diminished to being quadratic. Now I'm going to run through one way to implement an in-place quicksort. Here I've provided the pseudocode. We're given an array of items and integers a and b, and this algorithm will sort the items between and including indices a and b. The first step is the base case. If there are fewer than 2 cards in the range, then it is already sorted. The next step is to create 2 pointers L and R, which will start at indices a and b respectively. P, which is the pivot, will be the item pointed to by L. Here we say that the next few steps will be repeated until L and R are pointing to the same item. We will start with R and check to see if it is pointing at an item that is less than the pivot, or if it is the same as L. If not, we move it to the left 1 index and repeat. When an item is found, it is swapped to position marked by L. A similar procedure is then repeated by moving L to the right. When the 2 pointers meet, they will be pointing at an empty spot in the array. Here we will place the pivot. This will have placed all items smaller than the pivot to the left side of the array, and all items larger to the right, just as I did when partitioning in the demonstration before. Finally, we call the algorithm again on the less than items, which will be those from starting index A to the pivot, and on the greater than items between the pivot and the last index B. Let's run through this once. I start with array S, given indices 0 and 7. I place my pointers at each end, and I choose my pivot to be the L item. Now I move R to the left until I reach L or a value less than the pointer. I stop at 4 because it is less than 5, so I swap it with L. Now I'll move L to the right, again until I reach R or a value greater than the pointer, which happens to be 9. The 9 is swapped over to R. Now we start again with R, moving it to the left until we reach the 2. After swapping this, L is moved. There are no larger values, so it reaches R. This is where we will put the pivot. Notice that all values smaller than the pivot are to the left, and all values larger are to the right. Because of this, we know that the pivot will not move anymore. Now that we've partitioned it once, we will call quicksort again on the less than items, which will be from index 0 to 2. We don't care what the rest of the array is at this point. L becomes the pivot, and we start by moving R. However, in this case, R is already pointing to an item less than the pivot, so we can simply swap it. Now we move L, which moves all the way over to R. Put the pivot back, and call quicksort again on the next section. As with before, when left with one item, it won't change position, so we know it is in the right spot and can move on. After we finish the left side of the array, we move on to the right, which were the greater than items. This process continues until all of the array from A to B has been sorted. Despite having a worst-case runtime that is quadratic, Quicksort is still usually one of the fastest sorting algorithms.